Okay, let's talk about friction. Um, so far, we've been assuming that we can neglect friction when solving problems. And this is nice in that it simplifies the math, but it's not very realistic. So let's see if we can build up a simple model of friction that we can incorporate into problems to give us a little more realistic picture of how the world works. So what is friction exactly? Well, it's a force that opposes motion. Um, we're going to talk about two kinds. There's a static friction. It's basically the friction when things are not moving. And there's a kinetic friction associated with things that are moving. And you can kind of visualize this if you imagine a box or something and you're pushing on it with some force. Uh, the floor, the surface that this is going to push back on that box with a force that's equal to it. And that force of static friction is going to match your pushing force. So if you increase your pushing force, this static friction will increase. If you increase this more, this will increase to exactly match your applied force up to a point. Eventually, this thing will start to move, in which case, if your pushing force has gotten sufficiently large, um, and in that case, the friction will now be kinetic friction, and it will actually be a little bit smaller than the maximum static friction. And we can represent this in a graph that's actually kind of useful. Um, so imagine this is our pushing force, this is our force of friction. So initially, you push on it, it's going to push exactly back. Our force of friction is going to match the applied pushing force. You push harder, it's going to match up to a point. If you apply enough pushing force, it's going to overcome the force of static friction. And actually, after that, the kinetic friction is going to be a little bit less than the maximum static friction. So you can think of this as being sort of the kinetic moving, and then this over here is static not moving. And what you can take away from this is that basically the static friction is going to be as big as it needs to be to keep the thing from moving. So static friction is as big as it needs to be. And provided that it can be, that large. Um, if you overcome it and it starts moving, then you get into the kinetic friction regime. And it turns out that there's a really simple mathematical relationship between um, the friction, the force of friction, and the normal force. And it's this. The force of friction, and I should say this is an empirical relationship, not so much a mathematical relationship. This is something that's been observed. Um, the force of friction is equal to the normal force times a constant. So it's proportional to the normal force. And this constant is called the coefficient of friction. And we use the Greek letter mu for this. Looks sort of like a U. Um, and we had been doing these problems and talked so much about the normal force. Well, this is where it comes into play. If we know the normal force and we know the coefficient of friction for some surface combination, we can find the force of friction. So for all the times when I've been trying to emphasize to you, the importance of including the normal force in your free body diagrams and uh, trying to be careful about being able to calculate it like on an incline and in situations like that. This is where it will come in handy. So we'll use it to uh, find the force of friction. So a couple more things about this mu. There are two types. So there's a mu s for static friction and a mu k for kinetic. And uh, so you can imagine a material will have a different coefficient of friction depending on if it's stationary or if it's sliding. And uh, as you would expect, mu k is less than mu s. So let me give you a chart from your text to give you a feel for the magnitude of this coefficient of friction. So for some different materials, you can see something like tires on concrete can have a coefficient of static friction up to 1, and so that's pretty large. But notice like the kinetic friction is smaller, significantly smaller, and that gets at why it's dangerous if you're driving and you get into a skid because your tires have less grip when they're skidding than when they're not skidding. Um, and so this would be a pretty big coefficient of friction, and this is in contrast to something like ice. It's much smaller, 10 times smaller, which makes sense. We think of ice as being slippery, and when there's ice on the road, that's a hazard. Um, but interestingly, something that's a lot slipperier than ice even is your joints. So like nature has engineered some really exceptionally slippery surfaces inside your joints, which makes sense because you don't want those surfaces to wear out. So hopefully this kind of gives you some ideas about the relative coefficients of friction for different situations, and kind of where we're headed next is how do we apply this to solving problems. So that's where we're headed.